Okay, perfect. Okay. Yeah. So at the moment they are holding sort of the world record of the highest intensity laser in this domain that we have here. So it's really the cutting edge system that we have in this area. So like all the great beginnings, they have humble sort of start, and so has this field. So it's all started back in, let's say, 1960 by Maimon. And it's a very modest free running system. So it produces almost a kilowatt like you have in your oven. So it's almost a similar power. Since it's a free running, it was almost a millisecond duration. So it's not a short pulse anymore. So you get very modest light intensity, 10 to the 8 watt per centimeter square. That's kind of intensity we have. So fast forward from 1960 to, let's say, 6 decades, now we are having, instead of a kilowatt, we have petawatt lasers. So there's a normal gain in the peak power. And all that happens just because this parameter, this millisecond, shrink down to 20 femtoseconds. So it's very short pulses that we can have now on the lab scales, and that pushed the frontier by several orders of magnitude. So the peak intensities nowadays we have is 10 to the 23 watt per centimeter square, and it's order of 10 to the 14 jump in what the very first laser saw. And that gives us opportunity to really do very high energy density science, which was not even thinkable at that time when the laser first came into the picture. So how do we normally feel this petawatt laser in our day-to-day life, in the common sense perspectives? So the gigawatt is all we are very familiar. Terawatt, of course, because now we are aiming for $1 trillion economy. So there's 10 to 12. So petawatt is 3 more zeros beyond that. So that's kind of peak power that we are looking for. So our nation, the total grid capacity that we have, that we consume is a fraction of a terawatt. So this is, if you see the petawatt laser, they're still 1,000 times more powerful than what we need for the entire nation. But of course, the catch is that your devices will be active only for a very short time, and they're dead for a very long time. So it gives you very small belief of happiness to do very extreme science, but you have to time it very well. And that also means all the dynamics associated with these interactions are very transient in nature. So they survive for very short time. So you have to do very dynamic time-dependent measurements to dig out the physics from the systems. I mean, another way to feel this intensity, that 10 to the 23 that we're talking about, is, for example, if you are on a very sunny day, you are standing in the seashore with, let's say, 1 by 1 meter solar cell in your hand. And if suppose the solar cell is almost 100% efficient, you'll get close to 1 kilowatt power in that solar cell. Now, imagine extending that solar cell all the way up to the size of the Earth and focus all the light that you get to a fraction of your hair thickness. And that is kind of equivalent intensity you will have, which is what the petawatt lasers are offering you on the tabletop right here. But again, at the caution that this is a CW and we have a pulse system. So where we can find these lasers now, they are distributed all over across the world, except a few continents. And because of this recent, the CPA technology that really pushed, so previously all the big lasers were located in the national lab facilities because they could afford it, not at the university scales. But as this technology sort of shrinks down the laser system, now you can have very dense map across the world. And of course, India is not exceptions. We have many 4 or 5 centers which are doing this extreme laser science. So it's really exciting time to do this high field science back here in India.
Not in Australia?
Done in Australia even now. There are some groups which do those theory, but no laser. This, yeah, none here, none of course here. 1 or 2 places in Canada, but predominantly North America. And so, yeah, this is the belt where it is growing up. Of course, China is now catching up very fast. Like all the areas, they are at the moment they are pushing for 100 petawatt, where the world is at a petawatt scale. So they are already planning for that scale. So So when it comes to doing this extreme science, there's just one aim that people are passionate or that are pushing the frontier is to get the maximum intensity that they can to these interactions. And when it comes to intensity, it's mostly the 3 number that you have to dial and to optimize. So the energy, of course, comes with a financial cost and the practicality. So you can't really push this very much. But on the area and the time is you have to sort of deal with the diffractions what the waves are offering, or the best that you can do. So it's sort of the 3D confinement problem that people are trying to solve. So in the time domain, if you are working with the optical laser pulses, you can squeeze it down close to a couple of femtoseconds. That's in the time domain. In the spatial domain, you can go order of the lambda by focusing the light twice. So that's the domain both in space and time that we have. In the time domain, of course, if you want to go very close to a single cycle pulse, which is let's say 3 femtoseconds, the challenge that we have is we need a lot of bandwidth, because in the Fourier domain, the delta t is constrained by what the bandwidth that your laser offering. So the most often you have to actually go for active bandwidth increasing, and there are a lot of nonlinear techniques to do this. So at the moment we have the state of the art is close to 4 femtoseconds, sub 4 femtoseconds in the time domain that we can push these pulses. But when you're trying to do these pulses, your spectrum is actually very broad. So your original TIFR laser is somewhere here, 800 nanometer, and the bandwidth is about 30 to 40 nanometer. But to reach this single cycle, you have almost generated so-called white light. So it's not very clear what you define as a single cycle, because now you have all the continuum as a part of the spectrum. So there's some sort of a trade-off. So the blue curve is the spectral, which is this axis, and the red is this axis, the phase based on the spectral phase. So ideally, you want the phase to be flat, so you can compress it down to the diffraction limit. But if the phase is not flat, then you have the uncompensation left in your in the pulse here. So you see this tiny bump here in the time domain. That is appearing because your pulse is still not ideally flat in the phase. So the more sort of jumpy this phase would be, more structures you will see in the time domain. Okay, yeah. So that's the story in the time part. In the spatial domain also, you can focus down these pulses close to a micron ideally, and people are doing it routinely. But the problem with these big systems is, you see, this is this whole area is consists of 4 petawatts. So the laser actually goes through thousands of passive and active optics, and each one of these stages you add up aberrations to the wavefront. So when you measure the wavefront, actually you have a lot of distortion from the baseline, and the peak to value can be as large as 3 times your initial lambda. And when you focus these pulses, somehow the contrast is not good here. But what you will have is you will get the central blob here, but you will get a lot of satellite rings far away from your central focus, and that will lower down your intensity that you desire. So you spend a lot of money to build these lasers, but when you focus it, you don't get what you are actually aiming for. So, so whenever humans have faced a problem, they have looked upwards, and so this case is also not exception. So it seems the trouble of the wavefront was very well known in the astronomy, and the ground-based astronomers, when they image the signals from deep sky, they face this the turbulence affected this wavefront here. Of course, when you're on the satellites, you don't face this, but you can't build large telescope back in space. So this was troubling them for long term. And you do this by looking at the so-called the wavefront sensor. So if you put a lot of series of lens-set arrays, you will see that the distorted wavefront will go randomly based on the wavefront distortion that you have. And to compensate that, you can actually put, instead of a passive flat mirror, you can put an active mirror, which shapes the mirror surface itself to compensate for this distortion that you have. So if you're lucky, you have a static distortion, which is not in this case. You fix your the distortion in the mirror, and then you're happy. But if you have active wavefront distortion coming, then you need to have a feedback loop to dynamically correct this distortion to get the best spot. And the first proof of principle was shown by this paper back in 1990. So this is the picture where they have, if you don't have the corrections, you get this blur. It's actually a picture of a binary star. But if you don't have this correction, you can never predict what you had without the correction. So that's the power of the wavefront correction that you have in this system. And that is what being implemented now in most of the high power lasers across the globe. So this is the wavefront that you have before the corrections, and this is the wavefront after the corrections. And you can immediately see that your both peak to valley and the RMS almost goes to pretty small scale. And the effect also sort of comes into the picture once you focus your beam. So this is your distorted wavefront, and this is your corrected wavefronts. And the scales are not the same. So here the intensity is 1 times 10 to 22, and this is 6 times larger intensity. So this is where actually you get back your 10 million price that you have paid into the laser by putting this system. So we have one more similarities sort of that we can inspire from the high energy. Yes.
What do you use as a reference? Because when you do this in astronomy, you have to use
look at the nearby stars. Yes.
Something like that as a reference to correct your wavefront.
Yes.
What is the reference here?
So here what we have is you monitor the focus somewhere here in the laser system.
Okay.
And then your deformer mirror is sitting ahead in the beam line. And then you start this looping, sort of trying to converse with the different actuators. And then you try to sort of reach a stable focal spot. Most often you can do it, but if you have so many vibrations in the beam line, then you cannot do sort of live real-time corrections. So there's a feedback loop which runs between your eventual spot and the correction optics.
And what is the typical time scale on which this feedback
loop? So the typical loop. So normally we lower down the power, and we run almost like 1 hertz system, and the convergence takes about 1 or 2 minutes to make the loop. Once you do it, then you go back to the 4 petawatt, which fires every 1 second, and then you're monitoring as you're shooting whether you are still there, or you need to do some corrections as the shooting goes on.
Just one more question. I noticed that this is in micrometers, and so the mirror that you're deforming, it is granular on scales much smaller than micrometers.
So mirrors have mirrors here moving sub-micron actually, because you're very far, and the wavelengths, the peak to value you see is order of 3 micron. So the mirrors have different Z sort of depth. So you can it's more clear here in this cartoon that we have here. So what you have is a lot of actuators which are sitting behind the mirror, and they're pushing locally, very locally, the membrane. And then you have a small distortion in the mirror wavefront.
Yeah, but my question in astronomy, again, I've seen it's like of the order of a centimeter also, each of these.
Yes.
In your case, is it much smaller than a micro?
So here, of course, based on the constraint, the price that you have to pay. So ideally, you want the actuator density to be as large as possible. That will give you very fine local adjustments. But if you see, luckily in our case, we don't have very localized distortion in the wavefront. We have this broad global. So we can still have the typical DM system will have 50 to 100 actuators over a beam size which is 50 centimeter, and that's enough for this purpose. Yes.
Sure. Yeah, might help if you say what is the actual size of the laser. People think it's all like a laser point.
Yes.
So specify what is the actual.
Yeah. So once you go to the petawatt scale, of course, these are 50 centimeters beam. So 50 centimeters. So, yes.
So it's half a meter laser. Right?
Yes.
So you have 50 centimeters. Yes.
Later on, you focus down to micron. Yeah. Yes. So
in the lens, yeah. Or lens scale maybe centimeters. 100.
Yes.
100 microns would be great, but you don't pay much more money.
So this spot that you're getting is coming from a let's say, half a meter beam going down to 2 micron.
You should just say half of my size.
Yes. Yes.
Okay. Thank you.
So it's all limited by the fluence, the damage threshold that we have on the mirrors. If you go for, let's say, 100 petawatt lasers, 10 times larger, all you have to do is expand the beam, pay 100 times more price, get a bigger DM mirrors, So in principle, there's no limit. As long as you can keep expanding the beam, it's fine. But of course, the prices are exponentially higher.
That is the size of this beam of the entire wall, 100
The beam size or?
Yeah.
Yeah, of course, of course. So because this is a meter, so that will be 100 times larger. So, okay. So one sort of, because lasers have evolved, we saw this 10 to the 14 orders of magnitude enhancement in the peak intensity. And we have very similar sort of analog in the high energy physics domain. So whenever we have sort of a next generation of particle accelerators coming, let's say from Van de Graaff to cyclotron to synchrotron to LINAC and let's say all the way to LHC, the scale of physics changes, and thus also push the frontier to the next energy scale, and you can explore new physics. So that's sort of going on in the particle accelerator physics. We have something similar, our own Levingston plot. So here also the lasers have evolved as a function of time, and the peak intensity have gone up by several orders of magnitude. And by doing this, we have also changed the interaction regime of what the matter is exposed to this light when we are changing the intensity. So back here, 10 to the, let's say 10, we are dealing with a normal regular matter. We do all the nonlinear optics in this domain here. Once you go, let's say beyond 10 to the 12, 10 to 13, you start ionizing the system and you're dealing with the regular plasmas. Once you go 10 to 18 and beyond, the mean energy in the system in the electron is actually relativistics. That's the domain we call it as relativistic plasmas. Once you go beyond 10 to 24, the lightest ion that we have, a proton, that's also become almost same as the rest mass. So that's also domain is yet to achieve, but it is there on the wish list. Someday this point will go here. So right now we are here. That's the state of the art at the moment, and we can explore a lot of relativistic plasma science. Is still in the electron domain, not in the ion domain, and we'll see some of the examples what happens when we do these interactions in this area. So obviously at this field, the light field is highly non-perturbative to the most of the atomic levels that are known to us. So if you take a modest 10 microjoule focused down to micron, the intensities can be few times 10 to the 16. The equivalent laser field would be about 10 to the 9 volt per centimeter, and this is somehow similar that the electrons is experiencing when it is bound by the Coulomb potential in the atomic systems. And obviously, if you go, let's say, a couple of orders of magnitude, then this is highly dominating scenario from the light perspective. So electron is no longer listening to the parent nuclei; it's actually listening more to the light field, and you have sort of very instantaneous ionization in most of the systems that we have. So once we have the free electron, then let's start some very basic pictures. What happens if you see this interactions at the low intensity and the relativistic intensities? So normally, if you come up with this modest 10 to the 13 light, your electron is simply doing either Rayleigh scattering or Thomson scattering based on system is bound or free. And if you look at the electron trajectories and the momenta, it is purely oscillating along the E vector. B is not doing anything because it is simply clamped down because of V by C factor. But things change once you go to the relativistic domain, because then your V is almost approaching the C, and the V cross B term is no longer very silent factor. It actually becomes as strong as the transverse component. And if you see the Py, which is the transverse from the E, and if you see the Px, which is coming because of the V cross V, they are almost on the same scale. So you have almost similar momenta, both in the transverse and the forward. And you can see, in contrast with the low intensity, which is purely oscillatory motion, now you can see actually the electron is actually drifting along the K vector, and you have some forward motion because of the laser field. V is electron, which is just oscillating by the light field. And if the B is very small, it doesn't do anything, it just oscillates and does classical Thomson or Rayleigh scattering. So that's always happening. Okay, so we can also define sort of mean energy into the system based on this V or the Q or velocities. And it is simply given by this I lambda square scaling here. So this term is the Power motive energy in the MeV, and this intensity is defined in the 10 to the 19 watt per centimeter square, and the lambda is in micron. So the typical rule of thumb is if you have 10 to the 19 watt per centimeter square intensity, and if you deal with 1 micron infrared laser pulse, your quantum energy is about MeV, which is the relativistic energy domain. And once you have this system, actually you could excite, you can open many pathways from a simple taking 1 electron volt optical light pulse. So that's the sort of a beauty of the system, that all you do is you start with 1 EV photon, but not one, many of them. So that's the power of the collective phenomena, that all the light field is sort of confined in this 3D volume that we have. And because of this extreme field, you get very energetic electrons. And if you have a medium around, the electron can scatter with the ionic core and give you a lot of high energy bremsstrahlungs. On longer time scales, the electrons can give energy to the heavier ions. So that's also one channels. And if you tailor your targets, you can also aim for some fusion reactions like DD. They're also on the table. So it's sort of one stop, one single window clearance for many sort of species that one can explore in this scheme. So, so far we have seen mostly light interacting with a single particle picture, but in reality, what we are dealing with very high density systems. So that means the phenomena are mostly governed by the collective response of the plasmas and no longer the single charged particles here. So the light dispersion is sort of governed now by the plasma density or plasma frequency that we have. So that means your K vector is allowed to be real as long as omega is larger than omega p. So that means for a given laser frequency, you have a maximum density or plasma density where the laser can go. There's something we call as a plasma critical density, after which you have to reflect back. So for normal TIFR laser, which is 800 nanometer, this density is about 10 to the 21 watt per centimeter square, and beyond which the laser has to turn back. A very simple example that we see in our day-to-day life is the atmospheric ionosphere that we have. So the density there is about 10 to the 6 per cc. So this is critical enough to nicely reflect your radio wave, which is megahertz. But if you're dealing with the satellite communications, which are much higher frequency, let's say in gigahertz, this is no longer, so it is sort of underdense, and the signals can go through across this ionosphere. So based on this, we can sort of divide two regimes of interactions. One we call as underdense plasmas, where the light is allowed to go through, where the density is lower than the critical density. And this, if you shoot the laser in a very low density gas jet, you will see the channeling form as the laser goes through channels and propagates for long distances, and people do a lot of guiding in the systems here. In contrast, if you go to the solid density plasmas, where the densities can be 100 times larger than the critical density, you form very dense localized plasma right at the interface, and where a lot of absorptions happen and the laser has to turn back. There's no transmission in this case. So the question that we are asking is, can we sort of surpass this critical density and go beyond the constraint of the plasma critical layer that we have? And the answer is yes, if we explore this relativistic channel. So if you look at the plasma sort of frequency, it normally depends upon this plasma density and the charge and the mass. But the moment we start hitting the electron, the bulk electrons to relativistic domain, we have to also worry about the Lorentz factor to put into the mass here. And what it does is essentially slows down the plasma response time based on how much you are hitting the system. So if you take the standard state-of-the-art laser that we have, we can actually push the gamma close to 10 or even beyond. So that means this factor can go down by factor 10. And there is a possibility of actually going beyond the critical density that normally we encounter. So this is something known as relativistic transparency. So normally we have underdense plasmas where the density is lower than the critical density and light just walks through. Then we have the overdense, which is we have the reflections, and the transparency is sort of somewhere in between, where you're allowed to go through, provided your gamma is large enough to lower the barrier and the light can walk through this critical density surface. And this is what the dynamics of the transparency looks like. So you initially start with the opaque target, and as the laser heats up the electrons, your gamma goes up, and at some point, this condition is satisfied and the laser is allowed to sort of start transmitting. And then you have transparency happening at later time scales when the pulse has actually hit up the plasma a lot.
Necessarily.
So if you pulse
Otherwise,
is,
the
yes,
other thing might help.
yes. So the two constraint is, of course, the pulse duration, how long the pulse is, how much energy you have, and what is the thickness of this target. If you take really thick target, then of course it will take quite long to heat up the entire volume, and maybe you don't have that long pulse. So that essentially drives that you can actually use very thin targets to do these interactions. Otherwise, it's not going to happen. So so when the transparency happens, the clear signatures are that you will see a sudden dip in the reflections because the plasma is no longer opaque, actually it is transmitting. So your reflectivity will drop in the time domain. And similarly, you will see a sudden jump in the transmission because now the plasma is sort of transmitting the light, and you'll see the transmission coming up from the systems. So just keep this in mind. We'll take a small detour and then come back to this problem shortly. So what is the sort of the big aim that we are trying to push this field is, so we have this, let's say, petawatt laser, and we have this enormous field at the focus, which is just few micron volume. So the field that can go easily, let's say, teravolt per centimeter. Of course, this field is not a DC field, it's oscillatory field, it's swinging back in time every fraction of femtoseconds, but it is a very large field. So the question that people are interested is, can we somehow take advantage of this field and accelerate electrons to very high energy just by interacting with the light field itself? And the answer is no, because there's these two guys, Lawson and Woodward, they come up with very simple calculation to show that it's indeed not possible to have a free electron accelerated with the light pulse unless you do something different. So this is what happens. So if you just have a plane wave interacting with the electron, what will happen is the electron will nicely listen to the laser pulse, but as the laser pulse is gone, it comes back to the same zero momenta, so you don't gain anything. And all you have to do is sort of somehow violate this the symmetry that you have. So if you somehow break, there are many ways of doing it, somehow break the symmetry of laser pulse rising and then going back to zero, then you have a chance of getting a net energy gain from the system. One sort of smart way to do this is to play with the ionization potential of a system. So for example, you take a very highly charged state hydrogen-like system, in this case, let's say vanadium 22 plus. And since you're dealing with the very last electron which is left in the core, the ionization potential is large. It's almost a keV, so you cannot really ionize like normally you do EV scale. So that means the electron has to wait for the laser pulse to rise up to the maximum. So you are only ionizing at the peak. You're holding like share market. You're holding your gain and then releasing it only when you have the maxima, and then you actually gain the maximum energy from the systems. And in this simulation, the group have actually shown that if you time your ionization at different phase, then you can actually get much different energy boost from the system. So that's one way of sort of beating the Lawson-Woodward scheme. But so far, there is no experimental evidence in this area, obviously, because the constraint is you have to deal with very low density systems, almost shooting one atom at a time. So the flux that you get is negligible.
Can I ask a question here?
Yes.
Sorry. Sorry, Jerk, you were saying something?
No, what's the reference?
That's
As
yeah,
PRL
because I have to fit. It's a PRL 2002.
2002, yeah.
This is one Chinese group, and Anthony is trans, I think from MBA.
Okay, yeah. So, can you explain the experiment again? So you have that already ionized vanadium 22 plus.
Yes.
So you've done that through some chemical ionization, or what kind of ionization?
So this,
how do you prepare that beam?
yeah, you pre-prepare. So you can have, let's say, second pulse. You can have two pulse, one pulse
Okay.
for the deep core ionizations that people can do with X-ray FEL, for example.
Okay, free
Or
electron laser.
FEL
Right.
plus IR combination. So you can
Right.
think of this system.
Okay.
And then come with the second pulse to just initiate ionization for the last remaining one.
So what happens there? It waits in
So-
time,
Yes.
right? It builds up,
It builds up, it waits for the fields to come up,
right?
because initially, as long as the fields are low in the early cycle,
Right.
it doesn't listen to it. It's still bound to the core.
Correct.
So it waits for the potential to be at least KV
And then,
scale, and then it
release.
releases. And
So
then-
you're saying that transfer of energy happens at the peak.
yes.
right?
So when you ionize at the peak, then you're not going this cycle of this low energy
Right.
rides. So you start with the very high fields, and that breaks the symmetry. And then you end up getting a net gain. So your final gamma is actually non-zero.
Yeah, actually, this cannot happen. Just thinking about it.
Hmm.
Because 22 plus is what only by, not just by, it has to be collisional in some sense, right? I mean, it has to be, you have to have a dense system and then you strip off. So there's a statistical thing about how exactly, or can you just produce specifically only 22 plus?
Yeah, I mean, for example, this is the theoretical exercise, but what you can
It's
do
theoretical.
is a theory paper.
Okay.
Yes, so experimentally, no one has.
But otherwise, you have to have a dense system where there are lots of collisions by
Yes,
these electrons
yes.
which have been ionized already.
Yes.
And you find some fraction of these ions which are in the 22 plus
Yes.
state.
For example, in pelletron, we do this stripping thing.
Yes, yes.
We can very nicely control the.
True.
I don't know till what scale we can go, but with oxygen, for example, we routinely see this stripping up to 8 plus, 9 plus.
Okay.
So 8 plus. Okay. Yes.
You can actually
Yeah,
produce.
sorry.
You can actually
It
produce.
will, I mean, it will saturation, for example. Let's. Yeah.
I mean, if you have a foil and you have, well, I mean, not just that, you need to have a dense system where lots of collisions happening and a fraction of the ions are in the 22 plus state. And they are, but necessarily only singularly 22 plus is unless you separate them out.
So with the dense system, the problem would be that you don't want any background plasma to come into the picture.
But how would you produce? Oh, of course, this theory.
Yes.
But in a realistic system, how do you produce one?
I mean, you can go for FEL, for example. You could strip all the way up to.
Yeah, but then there are cross sections and
Yes,
stuff like that.
yes,
So it's
yes. So
you have only.
You'll end up having an
22
ensemble of different
hanging
charge
off there.
distribution. Yes, you'll have an ensemble of charge distribution, and then
Correct.
yes,
You have to separate them out.
yes.
You can produce at relativistic energy, fully stripped.
What kind of?
Like say 1 GeV per nucleon,
Yes.
type of thing, you can fully strip uranium.
But can we control like 20 plus, 21 plus, 22 plus?
You can.
You cannot do that, Is it possible?
Yes, once you have such high velocity, then fully things are.
What's your distribution of that?
There will be a distribution.
So that's what it's. There is some who are ready to plus and some.
And we can have enough charge.
Selection goes.
Can we have also the charge in the beam? Can we have a charge also in the beam? It's not single particle that you're talking about. Maybe.
You can have hydrogen like uranium.
Okay. Maybe we should talk. Yeah.
Okay.
Yes.
I'm
Yes.
just trying to understand the process here. So is it for radiative ionization, or as Ravi was saying, it's collisional as well?
No. So the problem starts with you have this system V22 plus. It is given to you.
It's a theory.
Yeah. So this V22 is what you have, and then you come with a second pulse, or let's say your main pulse, and then you're waiting for the ionization of the core level electrons. Yeah, of course, if you do collision, then it's also in
Just to have a comment that this is very common, either 22 plus or 23 plus, all depends on their acceleration energy,
Mhm.
and you select with a magnet. So either 91 plus or 92 plus uranium also people do is very common in big accelerators, and even ECR plasma source, you can produce highly charged
And we
ions.
can have good charge.
Yeah, you can select with a magnet.
For example, suppose we want to.
Yeah, it's very common. You can do it. Yeah, it's selective. Yeah.
Yes. Yes.
Okay, let's proceed.
Yeah.
Thanks.
Okay. So so that's sort of one way to go. But of course, this is looking at the single picture. The other way to break the symmetry is just to have a simple foil, and that will. So instead of so imagine your laser beam goes through at some angle. So you have some z component along the k vector in the forward vector, and then as the laser reflects off, you sort of shut the interaction to go further. So what they are doing is, this is actually experiment. So they have a laser pulse and they have the beam from a LINAC, let's say, tens of MeV, and you synchronize these two pulses and then let them meet on the mirror. So the mirror is just a very thin foil. Electron will go pass through this the foil itself, and then what it is experiences is only the partial part of the pulse as it going through this foil. And when they do this, they are measuring the electron spectrum after the interactions. And what they are seeing is, so the blue curve is the inherent broadening of their LINAC beam. So the bandwidth is, let's say, few keV. And the red is the spectrum measured after the laser pulse was there with the foil. And we see the very tiny energy gain. So some sort of a proof of principle experiments. And so the broadening or the small tiny gain doesn't happen if you have just a laser going through without a foil. So if you don't break the symmetry, if you have just a laser going through without a reflections, then you don't get any energy gain to the system, and you have sort of the the Lawson-Woodward criteria that was specified. So that's sort of one scheme of getting around and then coupling light to the matter, to the electrons. But of course, the limitations are because the interaction range is very limited. It is only working at this interface where the light is reflected. And the secondary, you need to match these two beams, electron beam and the femtosecond pulse. So there's a spatial temporal matching that comes as a sort of constraint. So can we do better than this? So the answer lies by default into this transparency picture that we saw before. So what's happening here is the transparency is happening only for part of the pulse, as we've seen. Initial phase is the reflections, and half of the pulse is actually transmitted, or fraction of pulse is transmitted. So we have already symmetry broken here. We don't have the full laser pulse transmitted. We have part of the pulse which is transmitted. And since the electrons are already heated to very large factor, so the gamma is already very large. So that means electrons are almost moving with the C. So there's very little dephasing happening with the light pulse and the electron pulse. So what we saw in the simulation that so if this is your foil and it should be the laser pulse, blue dots are the electrons. And when the transparency happens, the electrons are almost moving with the C. And the C, so your laser field is oscillatory, but if you move almost with the C, you almost see a DC field. So you sort of get advantage of this being almost in the same phase. And of course, you don't have to worry about spatial temporal matching because it's inherently there in the system. You have accelerated electrons from the same pulse. So there's spatial mapping and the temporal mapping happening at the same time. So we tried to sort of explore this possibilities and then see can we do some acceleration by the laser pulse. So, but yeah, as Ravi said in the beginning that this has to be done with very thin foils, tens of nanometer, 100 nanometer, because the laser pulse is finite. It has to do the transparency when the pulse is still there. So we need to shoot very thin foils to do this experiments. Freestanding, again. There has to be nothing. So so this part we want ideally vacuum. So the laser should interact purely with the electron or with no background around. So, but of course the problem comes, we can't do theory, so it has to also be experiment. So the problem comes when we want to shoot very thin foils. The trouble comes when we see a normal laser pulse in linear scale. It looks very nice, very well behaved. We can do the experiments. But the trouble comes when you see in the log scales. So it has, unlike an ideal Gaussian pulse, it sits on this broad, this DC background, we call it AC. And also it has a lot of spikes, the femtosecond pre-pulses. In some sense, it is good. We want pre-pulse to improve the coupling and a lot of other things. But especially for this experiment, this is actually a disaster. We don't want the pre-pulse to ruin the nanometer foil. And we have seen that if you are at very modest intensity, let's say 10 to the 17, 10 to the 18, not even 20, you end up forming very large pre-plasma scale in. The scale that we have is 50 microns. So forget about nanometer foils. So they will not survive. You will simply blow the foil. So we need to clean the pulse in time domain before we think of even doing this. So one more problem. So now last time we look upward, now we look downward. So last time we saw the telescope, now we will see the help from a microscope. So the problem also appears very similar in the microscopy. So all the biologists, Sipto is not here maybe, but they do this routinely multiphoton microscopy. So if you want to see very localized high resolution images with a fluorescence microscope, if you just shoot with the laser, you get this broad Gaussian envelope masking your signal. And to limit this, you can actually do the intensity filtering by going for the 2-photon process. And this is the raw data, the picture that you see. This is the fluorescence from a single photon. This is the 2-photon. And you see very localized spatial confined or spatially contrast clean pulses in space domain. We want to try something in the time domain. So we want to clean the pulse in time by going for the second harmonic. And that's what we did. So you take the fundamental pulse and you do the frequency doubling by KDP, and then you get rid of the fundamental with the dipole mirrors, and you end up having very clean, high contrast 2 megapulse to do the experiments. So, so this is what the experiment was. So we have this high contrast 2 megapulse, which is shooting this nanometer foils, and you are measuring the electron spectrum on axis, so we're flying with the laser pulse, and we're also monitoring the electron beam profile as the interaction goes on. So these are the diagnostics that we have. So how do we know if the contrast is good enough? So so it should survive most of the foils that we are shooting, and we see the transparency doesn't come in unless we go down below 50 nanometers. So all up to 50 nanometers, the laser is holding very well, and we see the transparency coming only when we go below 50, let's say 20 nanometer, 10 or 5 nanometer. So that means we have very good sort of conditions for this transparency one. And when this happens, we see the dramatic performance in terms of the electron heating. So we have two sets of curve. So one set is within this gray band, which is the thickness of the foil going from 2 micron all the way up to, let's say, 50 nanometer, where there's no transparency. So these are opaque targets, and all of them sort of fall in the same zone. So this the energy gain is the same regardless of what thickness it is. But the moment you hit the transparency, the spectrum is much hotter. You gain much more energy from this transparency phase than the opaque case. And as a function of thickness, we could see that as the transparency goes up, your electron temperature and the flux actually goes up. So you can nicely tune the energy gain from the system by just changing the transparency fractions. So there's nice control in the spectral domain that we had. Beside this spectral, you also have a spatial domain features coming up. So for example, if you shoot normal opaque foils, you get this sort of broad homogeneous beam, electron beam. But once you shoot this transparency foil, you actually have the donut into the center. So you have almost a very low flux in the center, and you form this donut beam. So what it does is it scatters, the electrons get also scattered from the laser pulse on axis, and you have actually the depletion of flux on the axis. So to understand this dynamics better, we went for elaborate simulations with help of colleagues. Fayuli did most of simulations for this part. So we see, so this y-axis is the electron density, the critical density that we have, and the x-axis is the time domain. And we see that initially, so the black curve is for the opaque foil and the red is for the transparency foil. And we see initially they are almost going together, but as the gamma goes up and the transparency hits, we see a clear departure here with the opaque versus the transparency foil. And somewhere near the peak, so 0 is the peak of the pulse, somewhere near the peak, we see that the red curve actually falls below the 1. So that's where we have the onset of transparency. Y-axis is the normalized critical density that we are talking about. So density NC1, that means the laser is cut off. It is reflecting. Density lower than that, laser is transparent. So, yeah. So, and we see, of course, we reproduce the experimental results that we see also when the transparency is happening, we get much hotter electrons as we've seen in experiments. But more detailed actually analysis came when we look at the individual electron trajectories, and that's where we could see a lot of insight from what's going on from the systems. So from this picture, what we have is the x-axis is the laser propagation axis where we are shooting the foil. The y-axis is the forward momentum of the electron, and all the lines that you're seeing is individual electron trajectories as they have gone through the entire history of evolutions. So somewhere lambda equal to 20, this is where the target was initially, the nanometer foil target was there. So laser, you start with very low momenta, and then we see this phase rotation happening here. So electrons are actually going back towards the laser directions. And then the momentum actually drops. And this drop is because what we call as a sheath deacceleration. There is a retarding field sitting at the target rear, which is good for ion acceleration, but bad for the injection that we're trying. And once you come out of the plasma into the free domain, where there's just a pure vacuum, then you see actually electron getting injected in the laser field. And then you see the momentum suddenly spreads up to very broad. So you start with the px somewhere around, let's say 10, But as the interaction goes on, you see this much broader momentum space as the end of interactions. So at the moment, of course, we can't control individual electrons where it is going. So each electron have very different trajectories. But what we get at the end of the day, much broader momentum or energy gain than what we started. Yes, in the simulation we can.
No, in the experiment.
In experiments we can't. So what we have is only the far field. At the end of everything, what we have is a far field monitoring.
And another quick question for just a geometry. So you were measuring both the electron energy that is coming out and also the intensity of the laser light.
Yes.
So both are on axis. Like how is the geometry?
Both are on axis. So we have this tiny hole in our screen that lets the electron to go through, and then we have the screen to monitor the laser beam file. At this scale, no, because E is still. So what we have is electron is almost sitting as like a. It's almost. I'll come to that picture. So it sees almost like a DC electric field. So the B field comes and we see small deflections happening away from the axis. That is mostly for the low energy electrons. High energy ones, they have enough momentum to sustain on axis and they gain actually most of the energy from the system. Low energy ones, they deflect away from the axis very soon. So that's what I was saying. So we have sort of three phases. So the phase one is where the electron is actually injected back to the foil rear side. The phase two is actually retarding for us, it's negative for us. So only the energetic electrons to survive this decelerating potential will be injected, and the rest will be sort of pulled back to the target itself. And the energetic ones, once they inject it to this the VLA phase or the vacuum resurrection phase, they will go into this acceleration with light paths. So let me just go to this the last one. Yeah. So this is the picture that was shown. So here we are seeing instead of this individual tracking, we are seeing this two-dimensional XY space. So again, each line that you see corresponds to individual electron trajectory. The color represents the energy. So the blue means we have very low energy electrons, and the red means we have high energy electrons. So what we end up at the very beginning where the foil is kept, where the interaction started, we have mostly the blue dominated electrons, they're very low energetic to start with. The energy gain happens very small, so the gradient is actually very large. So you see the color immediately changing to the blue from blue to red. So that means most of the acceleration is actually happening when the electrons were injected into this VLA phase. And that comes this the magnetic field part here. So you see the spanning out of the blue lights, the blue colors. These are all low energy electrons. They get kicked away by the B field. But whereas the high energy ones, they still survive and they remain on axis throughout the interactions. Okay. So and of course in the experiments we see sort of a signature of this. So as the deflection is more dominant for the low energy, not for the high energy. In the experiments, we have the spectrometer has very small solid angle. It's only microsteradian. So that means electrons which are deflected away from the axis, you won't see them in your spectrometer, or you will see actually less of them in the spectrum. And that is what we see. So this is the blue curve is for the opaque foil, and the red is for the transmitted foil. But in fact, when we see the low energy flux, actually this flux is even lower than what we had for the opaque case. So that means we have actually not captured them in our spectrometer. They have been just deflected away by this speaker. Okay, so how much time I have? Maybe okay, because I was very slow. What? 10 minutes? Okay, maybe 15 minutes. Okay, let's see. Okay. So far we have seen this sort of two extremes, underdense plasmas where the light just goes through, and then we have seen the overdense plasma and the transparency in that system. But is there something in between that we can also look the ground? And the answer is yes. There is something we call it near critical density plasma. So it's sitting very close to the NC, but it's a fraction of NC, let's say 10% or 20% of NC. And the beauty of this system is that the laser is still allowed to go through maybe hundreds of micron deep inside. But unlike the underdense plasma, your absorption, local absorption is much larger. not as large as solid plasma, but it's still much larger than the what we have under dense plasmas. That means the you can form a sort of this very high energy density conditions in these systems, and if you give enough time, you can also form electrostatic shocks. The sort of a counter that we are seeing from the this near critical density plasma systems. Unlike solid, where the interaction is mostly in the skin depth or fraction of a micron, these systems are almost millimeters, sub-millimeters. So you can optically you can see. I mean, its diagnostic wise is very sort of unique system that you can see inside this dense plasma cloud. Otherwise, you can't see because of the scale length. So that's why it is very interesting. And to do this, what we had the question that we are asking with this NCD system is that suppose we have the petawatt lasers where you have this very large Lorentz factor. So far we have seen this playing role in the frequency domain, or let's say the plasma response time. But if you look at the time domain, which is just the inverse of the plasma frequency, the gamma is actually slowing down the plasma response. So what it will do is, when we say slowing down the plasma response, that means the electron job is to actually quickly overcome the cavity which is formed by the laser evacuations. So normally electron try to recompensate that and then quickly neutralize the plasma cloud. But if the gamma is very large, then actually this plasma response time slows down by the square root of that factor. So if you have gamma, let's say order of 20, then actually you can slow down plasma response time by square root of that factor. So that's we are trying to explore in this NCD system. So in the experiment, what you do is you take your petawatt lasers, you shoot into this dense gadget systems, and then with the density is about 10 to 20 or a few times 10 to 20, and then you are measuring the electrons almost on axis with the energies going up all the way up to, let's say, 20 MeV and beyond. And then you measure for the shock, for the proof of shock, you see the ion acceleration coming from the shock accelerations in the transverse side. So this is the experiment and the simulation that they look pretty much close to each other. So we see as the laser comes, we see this sharp plasma boundary formed because of the shock interface from the background plasma cloud. And in the simulation as well, we see this the shock boundary being formed in the radial directions. And as the time evolves, the shock actually expands with 2% of the speed of light. And there's a possibility that it can actually reflect the upstream ions which are sitting at the background. So in this case, this is just the shadowgram. So it's light intensity. So it's a probe which is going through. So it's a shadow of the plasma. So this color represents you have more transmission, and the black, sort of blackish or the dark bluish is less transmission. So there's a lot of opacity by the dense plasma cloud that we have here. That's what. So it's essentially the transmission of light through this plasma. That modulations we can't capture. This is limited by the resolution. Yes. So simulations can have very nice resolution, but so this would be because it's still under dense system. So this will be about hundreds of microns. Yeah, hundreds of microns. We can see. You mean the structures inside? The amount of density is very little. So that resolution we don't have. So the scale is in micron. So optically we can't prove it. Yes, simulations they can see 10 particles, 100 particles, but experiments, of course, we can't see those in the experiments. Okay, so the idea here is that if you heat up your bulk electron to a large Lorentz factor, what you are doing essentially you are allowing the field to be there, the electrostatic field to be there for longer term. That means the bulk heavy ions which were left in the cavity, they have time to actually accelerate and then gain energy from the system, which normally don't happen. So this again, all the simulation plot here. So this one is electron density at early time scale, and if you wait long time, the ions actually gain energy from this radial Coulomb field, and they form the shock boundary. And then you can see very nice this transverse electric field at the shock boundary, which can reflect the particle itself. So in the experiment, what we could do is we could probe this by changing the density of the system. So if you go to the lower density, which is close to underdense system, then we see again this classic filamentary structures and no shocks getting formed. And then when we measure the ion spectrum, we see no signature of shocks. That means both the helium and the proton have the same energy by charge ratio, and there's no signature of shocks appearing there. But the thing changes once we reach close to the critical density, the NC, so to say, and then we see this the dense cloud appearing, the spherical shocks coming up in the system, and we see now the hydrogen and the helium almost have the same energy, or in terms of the velocity, the hydrogen have 2 times the velocity of the shock front that we are getting from the systems. Maybe just 5 minutes if I can. I have 5 minutes.
Yeah.
Okay. Okay. So maybe I will skip the more heavier ion inertia. So with a lack of time, but so essentially, just to say in just few seconds. So if you wait for longer time scale, then you have also interesting physics coming from this high energy ions particle. Of course, they have their own time inertia, which is about a picoseconds, unlike the femtosecond for the electrons. But they do have also a lot of interesting physics that they can carry in picosecond time scales. And one of them is if you just see the emittance of the proton beam, or if you just see the sort of projection imaging from the proton beam, you could actually infer a lot about the sheath structure or the plasma structures based on your pulse is short pulse or the pulse is just a few cycles. And we see very, very drastic pictures. If your pulse is long, then the plasma have a lot of instability build up in contrast with the short pulses, and you don't see any instability. And you see almost like a perfect projection imaging pictures from the systems. So we do have sort of very broadband spectrum, unlike the accelerators. They're not monoenergetic in nature. So we get very broadband Maxwellian kind of energy spectrum. In most of the applications, people don't want it, but in sometimes it's actually sort of a bliss and comes with a surprising point. So the advantage with having a broad band spectrum is that as the time evolves, different ions of different velocity will separate out in the space or also in the time. So suppose we start with a very thin layer of proton beam with different energies. As the time evolves, you can actually separate out high energy ones streaming up front and followed by the low energy ones. So that allows you actually to do a lot of this chirp. There's analog of the chirp in the optics itself. So you have a lot of the chirping in the energy domain and the time domain. So you can do a lot of single shot plasma dynamics using these different energy structures in the proton beam itself. And one simple proof of principle could be you can have very transient currents going through some wires, and you can see the proton deflectometry in the transient current, and we could see that as a function of different energies, you can build up different charge dynamics, and you can sort of create this transient current, sort of a terahertz pulse that you can see in this wire. So normally the proton goes through this charge wire, and it sends the local field and it deflects away from the. So in the shadow you will see much broader width. So I don't know if you can see. The mesh is close to gigavolt percentage. So this is a return current which is induced, and the electrons are sort of this transient current. Yes. So yes. So imagine your wire is very thin to start with. If you just see a shadow of uncharged wire, you will see something like this thickness. But if the charge is going through at that time when the proton was passing through, you will be deflecting because of the fields there, and you will see much bigger deflections. And then you retrace, and then you can reconstruct the fields from there. Yes. So again, limited by the RCF, the radiochromic film that we are putting here. So the resolution in this case is about 1 or 2 MeV.
1 or 2 MeV.
Yes.
In 12 MeV.
Yes.
And when you say 2 MeV, also similar proportion.
So here, let's say, for example, we have 13, 11, 10. So these are like different bands of. One option would be if you can time the time your detector, and then like what MK does for the time slicing, then you can get very high resolution images, but not in single shot. So things can be more interesting if you have, instead of just a pure hydrogen, if you have, let's say, multi-species ions there. For example, if you have hydrogen, oxygen, carbons, what happens in this scenario? So when you have this mixed layer of ions sitting at the target rear and ready to be accelerated, we do see them in our spectrum. But of course, the proton being the the lightest particle and with the highest charge to mass ratio that wins the race, and then it appears at maximum energy. And then it's followed by all the heavy ions like carbon and oxygens and different charge states comes up. But it does follow very nice this Q by M ratio. So in the accretion phase itself. So what's happening in the experiment is that as the time evolves, your proton is actually at the upfront with the maximum energy, followed by different section of C6 plus, 5 plus oxygens. So you have different charge species which are sort of bunched somewhere in the distribution of this density contour. And what they can do is they can locally create a stronger Coulomb field, what the ions are normally experiencing, and they can sort of do very nice micro spectral bunching. And that's what we see in the experiments. So this is, so here we have different sort of spectrum. The green one is for the proton. The red one is for the C6 plus, gray is for the carbon 5 plus, and the blue is for the oxygen 6 plus. And instead of a normal falling spectra, which normally we see a very nice this modulation, the kink appearing in the spectrum. And the kink appears very close to the carbon 6 plus maximum energy, or the front of the carbon 6 plus velocity. The 6 plus also have a kink, which appears at the maximum of the oxygen 6 plus. So what you end up having is actually the different charge species layers are pushing part of the spectrum where this local bunching is happening. And you can actually modulate the local spectra. You don't make it monoenergetic, but at least quasi-monoenergetic in that domain. So that's sort of one takeaway lessons we can take it from. So with this, maybe just few seconds for the future that we have coming up in the cutout facilities. So we have very soon coming up this petawatt laser facility at the TIFR Hyderabad campus. The clock has already started, so it will take about 24 months for the laser to be physically being here. So this is the rendition, artistic rendition of the building we're supposed to be maybe in a year from so. So this is petawatt is a commercial system that we're getting from Amplitude. So it's about 20-25 joule 25 Tesla system. The beauty is, of course, you don't see this the spiky pre-pulses. Yes, it's much clean and gives you a chance to do more of this extreme relativistic clean interactions. We may have to still do the frequency doubling to shoot very thin coil, but we'll see. The wavefront is pretty good, but if you want to really squeeze, we need one deformer in this system as well to really squeeze all the petawatt has to offer. This is the experimental and the laser hall that we are that's coming up very soon. So the laser hall is about 30 meter by 16 meter laser hall. It is class 10,000 environment to make sure the laser don't burn the optics. It's also sitting on isolated floor. Make sure the vibrations are not affecting the laser pointing and other stuff. Since it's petawatt, we have to go for the complete radiation shielding. So it's like Lena hall that we have here. So it's a 1 meter concrete wall, 20 by 20, almost the experimental area that we have to do this high field experiments. In terms of the experimental platform, we have the beam coming. So this is the concrete wall. We have the beam coming from the laser hall to the experimental hall, and then it is delivered to multiple chambers. And each one of them probes different physics, underdense plasma, solid density plasma, critical density plasma. So they are very diversified experimental platform to do many experiments in the same facilities. So in terms of laser, we would be sitting somewhere here to probe this part of here. And we want to actually push the frontier from MEV to the GeV using this petawatt lasers when it's activated. And there are just a few couple of examples. So for example, one can do a lot of this underdense laser guiding wave field accelerations. And you can accelerate GeV electron beam, very monogenetic, unlike what we have seen before. Perfectly ideal for a lot of synchrotron-like accelerations when they wiggle with the charge beam. Or you can shoot very localized nanowires, and then you can do a lot of surface wiggling here by this transient field here. One thing that we wish to also have in long term is actually go beyond the optical probing and to really dig deeper into the plasma and what's going on, is to go towards what's called as a multi-probing. So apart from the optical probe, which is limited by this normal low density, critical density, ions beam, charge particle beam can go much deeper and they are only limited by the energy of the system. So we can have ultra-fast electron and the proton radiography, which will bring out all the field information because of charge deflections. We can have a complementary to this ultra-short X-ray dynamic imaging. So this will give us any contrast information. If there's any shocks deep inside the system, we can bring out the shock information from here. And we can have, the last one is a neutron. So it's also a very interesting picture. So this is from PSI. It's actually a statue of Buddha seen in the three domain. One is optical. You see nice brass, and then you see the X-ray. You actually see all the high Z, which is there. And then you see this wood. So there's actually wood sitting inside, which normally.
You see the Buddha smiling or not?
It is actually meditative. So Buddha will smile when.
Buddha smiled in 90.
Yes, yes. So this very low Z stuff which is hidden in this metal, you don't see otherwise with the X-ray or with the optical. So the neutron radiography will be sort of complementary to all the schemes that we are aiming. So with this, maybe I'll stop and take any questions. Thanks.
Thank you, Prashant. Thank you very much. A lot of ground was covered. I'll just ask a first quick question. Can we do with the X-rays? I saw the X-rays also coming out. So can we sort of use an X-ray probe to look at evolving chemical structures? Like we can think of experiments, very small scale experiments.
Yes.
But but we could do in principle with a tunability with a higher harmonic separation.
So with this, we are aiming almost monogenetic beam here.
Right.
So get almost quasi-monogenetic photon bunch to do this.
Okay, fine. Yes. Cool. Thanks. Questions? You can generate the
if it is
bandwidth.
GeV, if you just go with this Betatron modulations, we get about keV. So we get close to keV. Yes.
But the coherent radiation, the synchrotron, or the Betatron radiation, that will be at the level of particles.
Yes, few keV is possible. Yes.
By the way, you can also generate harmonics. You can go up to. These are truly coherent, driven by the coherent.
Okay.
They are actually true X-ray pulses, coherent X-ray pulses.
And the resolution, like what are the typical?
In spectral or?
Spectral.
In spectral domain.
Yeah.
That it will be about, I mean, it's not.
Yeah, line waves.
I mean,
what are the
harmonics are very sharp. Harmonics are Harmonics are down to EV. Suppose you're sitting at keV, they are down to EV. But if you go for the Betatron, they are about 10% of the.
Nice.
Yes.
Prashant, in your abstract, you talk about inverse Compton, upscattering of photons by electrons. So, what are they in gamma rays or?
So,
and what are the sweep photons and what are?
So that would be a little bit more tricky. So what we are actually aiming for is have this micron size electron beam, and then collide with one more laser which is about a micron size, and then you can inverse Compton scatter. So you can transfer energy from the incoming beam to the photon beam. That can, again, people have seen. So if your electron beam is, let's say, 100 MeV, the inverse Compton scattering, they have seen up to 5 to 10 keV photon. But again, this is
just to clarify, the electrons can be emitted by the same laser.
So optically,
And simultaneously you time it by scattering this, the rest of the laser vector.
Yes. So it's a 2-pulse experiment. You divide the beam, one to drive the electron beam and one for the scattering. Yes. 10 keV is what you are seeing. Yes. So at the moment, of course, the main problem is you need to collide two beams, and the lasers are, of course, going hundreds of meters. So there's always pointing fluctuations we see in the lab. So if you fire 100 shots, maybe out of 100, maybe 5 or 10, you have head-on collisions, and rest of the time it's actually side scatter. So these are slightly tricky. You need very stable ground to do this head-on collisions. Flux of the electron beam. So the electron beam, yes. So the size is about few micron in space. The emittance is about the divergence is about millirad. The charge that they have can go up to, it's not very exciting, but tens of femtocoulomb. So the charge is at the moment limited because
Okay. Any other questions? If not, then I'll pass on the mic to Ravi, who wants to ask a couple of questions. Okay.
Yes. I just wanted to ask you, well, just to make common cause with astronomers now, we should call it multi-messenger. It's not just
Yes.
multi-particle probing,
Yes,
it's multi-messenger probing, right? Because we're going to all sorts of particles
Yeah.
which control the plasma. And the other thing is that, these high energy experiments, we should tell the people that these are all few shot.
So that's, of course, it's
Me-
not like LSC where you're firing at megahertz or hundreds of
Yeah,
megahertz. This
I
is
mean, I think we should be very
1 hertz,
realistic.
0.1 hertz if you're,
And most of the experiments, it's okay for that.
yes.
approach.
Mhm.
Yeah. Should be okay.
Yes. Hmm.
So the nanophile experiment was how many shots at already?
So these are, we could fire, because each target you have to align is as a
So
focus.
each shot is one target is gone.
One target is gone. So you keep repeating the whole day, but if you're lucky, you get 30, 40 shots in a day.
Okay. And that's an experiment or
And then of course, it goes over, let's say, a couple of weeks. So overall, you have about 100, 200 good shots.
if you have a thick foil, the Pondermotive push of the electrons will actually pile up the electrons. So it will create, you can never reach transparency because it's just piling up
Yes.
against the wall.
Yes. So you have,
So that's the
So-
reason, one more reason why thick foils may not work.
so
It
you
has to be-
you initially saw that the radiation pressure actually pushing the
And
density up.
just for clarification, the skin depth at that wavelength
Hmm.
is larger than the nanometers.
Yes.
Even the normal skin.
Yes. So if you shoot the low energy pulse, you don't see the transfer.
And if the pulse has structures on the femtosecond rising edge,
Mhm.
then you have a serious problem because it
Yes.
will destroy
Yes.
the
Then you
pulse.
can pre-destroy and
Not
then
just picosecond.
yeah.
But great. Nice.
Thank you. There's one question by Lokesh. Yeah. Hey, Zoom kids.
Okay. Okay, this is very good. And what you said is a lot of applications looks like you are aiming for. But what is any new science, fundamentally new science which you can achieve?
Yes.
Can you plan something towards that with this?
So one sort of hot topic in this area is still people are trying very hard. One is to look for the corrections in the radiation reactions. So normally you have electron beam, which is very close to the inverse Compton scattering that we're trying. So you have the GeV electron beam, which is colliding with this very high energy laser pulse. And the electron will wiggle very strongly in this light pulse. So normally you have normal Rayleigh scattering, Thomson scattering without any corrections to the electron energy. But when they're exposed to such a strong acceleration, then the radiation reaction has to be considered. And now people are debating which model is a classical given by the Landau and all is true, or you have to do some QD corrections to that. So that's one area that people are looking for. But there are many.
Pair creation.
Yeah, pair creations, but that's so that will, that need to push beyond its 22. So this 1 petawatt may not be in the lab frame, may not be. Yes, 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 with the gamma.
With this gamma
Yes,
Because you have now 30 years ahead,
yes, yes.
not
Yeah. So yeah, I'm saying this. So one. Yeah. So one scheme that Eli NP, of course, Pali is not okay. So Eli NP have this flagship program that they want to create very dense neutron beam. So you have in the R process and S process. So for the S process, you need very large number of flux, instantaneous flux, to do this processing. So the beauty with these lasers is that you get very high. Of course, the repetition rate is very small, but you get very dense neutron beam, almost a sub-picosecond time scales. So there is one possibility that Eli NP, especially with the 10 petawatt laser, they're exploring. And there's something also that we are also trying with in collaboration with them.
Nuclear photonics where the
Yes.
gamma rays can actually induce transformation of nuclear.
Yeah.
You can study.
So the RNS process is one area that
Okay.
people are trying. Yes.
Okay.
Yes, exactly. So what happens if we have a bunch of neutron, very dense neutron? Then can we have this?
Okay.
Of course, experimental will be very tricky because you have to wait for enough number of statistics to see these images.
Okay. Thank you very much, Prashant, and thank you all for joining in. Let's give him a big round of applause. And all the best with this new toy on the market. So we'll all join you for some snacks in the canteen. So thank you. Monster.
Right. Yeah, but this it is sides. That thing was.
Yeah, it was slightly dense, so I could not.
It's wonderful.